Hi, discrete mathematics students. This is a video to introduce 6.1 set theory definitions and the element method of proof. So actually I expect you guys to read the section and learn a great deal from the reading itself. This video is merely designed to provide some examples that can help you with the homework. So on that note, let's display the homework here. Your homework assignment number 10 is going to consist of these 7 problems from 6.1, and I will post those on MyOpenMath and also send them to you by email as well. So the examples, so bear with me, I may stumble a little bit while making this video. I've already had one false start. This is a hard video for me to make. I'm using some software to display math text, hopefully in a relatively timely manner as I speak. I had to pre-type quite a bit, and I'm using some commenting symbols to make it appear as I speak, and that's going to be a little bit rough as I learn this for the first time. So the first problem we're going to look at is number 5. This should help you with number 6 in the homework. So we have two sets C and D that are defined before you. You can see that C is consisting of numbers that are 5 less than multiples of 6, and D is consisting of some numbers that are 1 more than multiples of 3. What we need to do is prove or disprove the following statements. In A, we have that C is a subset of D, and in B, we have that D is a subset of C. So essentially we want to know with these two sets whether one's a subset of the other or perhaps both. So let's have a look then. Whenever you're given a problem like this, the first thing you want to do is experiment by plugging in a variety of integers or whatever numbers make sense in the given context. So I want you to pause the video now and experiment for yourself to find out what C looks like and what D looks like, and you can make then your guess for the answers for part A and B. So pause the video now and do so. Okay, so having come up with your own answers, let's go ahead and start answering these officially. We've got in part A, turns out to be a true statement, and because it's true, we need to offer a formal proof that it's true. Now, when I prove things, I start with the word proof. I end with this QED symbol. Just by the nature of the software I'm using, this QED symbol is going to show up right away. We're going to fill in the contents in between here as we go. Now, since we're trying to establish that C is a subset of D, that C, the smaller set, needs to be somehow inside of D, what we're going to do each and every time with such a proof is start with an arbitrary element of that smaller set. You can use whatever variable you like. Here I chose the letter x, but we need to let x be an arbitrary element of C. Now, by the definition of C, what does that mean? That means that x has a particular format. In particular, it's 6r minus 5, where r is in some kind of integer. Now, we don't necessarily know what r is, but we know that there is some r that's going to make that true. Now, our goal here is to show that this x is also an element of D, which means it has to be 1 more than a multiple of 3. What we need to do is get this plus 1, and afterwards hope that we can factor out a 3 to get the right format. So I'm going to modify this 6r minus 5 to end up with a plus 1 on the end. So how can I do that? Well, if I want a plus 1, I can add a plus 1, and then I could subtract the 1 to compensate. And so the way I'm going to do this here, if I can type correctly, is that x is going to equal 6r minus 5. We already knew that. And I could rewrite that as 6r minus 6 plus 1. And the adjustment that I made to get that plus 1 gave me a minus 6. And that's going to allow me to factor out that common 3. Now, of course, you could factor out the entire 6, but our goal is to get a 3 in order to show that we have an element of D. And so I'm not going to bother factoring as much as I can. I'm just going to factor what I need. Now I've got 3 times some stuff plus 1. As usual, I like to do an extra little step here to define that 2r minus 2 is s. And that way I can write that x is 3s plus 1, and therefore an element of D. Now, that kind of finishes the proof, but we'll just clarify a couple other things here. We know that the x was chosen arbitrarily, and so that proves that every element of C is also an element of D. So it's not just that particular x, but because it was chosen arbitrarily, we don't even know the value of x. We were able to make use of the form as opposed to its value. That proves not only there's x, but x could be any element. So every element of C is also an element of D. And that's exactly what it means to prove that C is a subset of D. And that's going to finish our proof. So now let's look at B. Again, I'm presuming that you guys already experimented and decided for yourself what the answer was. And B turns out to be false, that D is not in fact a subset of D. So in order to establish this, we need a counterexample. And so once again, I'll have a little bit of a format here for my counterexample. And with a little experimentation, we can find out that 4 is in D, because 4 looks like 3 times 1 plus 1. So remember, if I scroll up here a little bit, D has the form 3s plus 1, so 3 times 1 plus 1. In this case, our s is equal to 1. But 4 is not going to turn out to be an element of C. And let's establish that with a little bit of contradiction. Let's suppose that 4 is in C, and then by the definition of C, that means that there's some r where 4 is equal to 6r minus 5. Now we can rearrange that equation a little bit. We can add 5 to both sides. And we can divide by 3. So that's equivalent to saying 3 is equal to 2r. Now, the textbook would divide by 2 and say r is 1.5 and not an integer. That's not my preferred way to do things. I will point out that this implies that 3 is an even number, and that's a contradiction. And therefore, 4 is not in C, and it follows that D is not a subset of C. All right, and so that establishes the answers for number 5, A and B. Now, an additional comment here, if you were asked to prove that 2 sets were equal, that C was equal to D, then the method of proof there is something called double inclusion, and you would have to establish both C is a subset of D and D is a subset of C. And so that would be a proof like in part A, only it would be twice the effort there. 2 different inclusions, 2 different arbitrary elements of sets in order to get both directions. Okay, so let's move on to problem 11. It's cold in my garage. I'm wearing gloves, and I think I need to remove those so I can type more effectively. So we've got problem 11 now displayed. So in problem 11, we have a universal set defined to be the set of all real numbers. And we're going to define A, B, and C accordingly. Now, we're actually not going to use set C in this video. You can see that this problem actually has several parts, A through J. And I'm not going to do a lot of these. I'm just going to do enough to experiment with the union, the intersection, the complement, and then a couple of these things combined. I encourage you to do the rest of these, and you should definitely ask me questions by email or on the forum on MyOpenMath. Or we can set up some office hours with Zoom again in order to discuss these problems. But I am going to do parts A, B, C, and J. J is actually the last one in the textbook as well for number 11. And for these, we only need sets A and B. Now, A is defined as numbers between 0 and 2, inclusive on the 2 side. B is defined as numbers between 1 and 4, inclusive on the 1 side. And we've defined unions and intersections before earlier in the textbook, and so a lot of this stuff in set theory ought to be a little bit of a review. But let's proceed anyway. So what is the union of A and B? Well, the union is going to be taking all of these guys together. These are two intervals and they overlap a bit. And so the smallest we're going to get is close to 0, and the largest we're going to get is close to 4. And so when we look at A union B, we're looking at numbers. Oh, and I've got a little bit of error here, so bear with me. Okay, we're looking at numbers between 0 and 4. So we start at 0, we end at 4. The numbers between 1 and 2 were actually overlapping there quite a bit for those sets. And those are getting absorbed in both. So we don't actually have a less than or equal to, because that would be numbers that are in the middle anyway. But the 0 is not included, and the 4 is not included. We can also write this in interval notation, which I'll do now. Is the interval from 0 to 4 with parentheses because neither endpoint is included. Okay, I'm going to move along quickly with these. So in part B, we have to look at the intersection of these guys. As we already mentioned, there was an overlap of these intervals between 1 and 2. And so we can write the set builder notation, x between 1 and 2, inclusive this time in the 1 and 2, because those are actually endpoints that we want to include. And once again, with interval notation, we can use the brackets to represent the inclusion of those endpoints. All right, for part C, we are looking at the complement of A. Now, I think I introduced this a little bit ago, a couple weeks ago, when we were talking about some induction proofs involving De Morgan's laws. So if you want to go back to your notes on induction, I had given an example in class and may have included something similar in a handout where you're doing a proof of an arbitrary but finite expansion of De Morgan's laws to beyond like just 2 sets. And so in that section we actually introduced the notion of complement, but it's also been introduced in your reading here recently. Okay, so we need to consider all the numbers that are in our universal set, but not in A. And so that's going to be the numbers less than 0 and greater than 2. And we can include the 0 because the 0 was not in A either. So let's have a look. There we go, less than or equal to 0 or greater than 2. And in interval notation, once again, using our parentheses and brackets accordingly. We always use parentheses on the infinities. But because we never include those are not numbers as far as we're concerned. But we have the bracket on 0 here and the parentheses on 2. Okay, so we've got then a little bit of a gap, and we jump down to exercise J, where we're looking at the complement of the union. And so the main thing with these is if you have a couple different operations, you just need to take them in sequence. And we're in luck because we already did in part A the union. And so we just need to take the complement of our answer there. And we can see that's going to be the numbers that are outside of this interval. So things below 0 and above 4. And because 0 and 4 were not included here, they do get to be included in our answer for part J. So we'll have numbers less than or equal to 0 or greater than or equal to 4. And in interval notation, as expected, there we go, and we're done with the problem. Okay, we just have a couple more examples left before the video is over. So let's look at problem 27, which is on the next page. I need to scroll for you. So I have a question: is this collection of sets, so this is a set of sets, is it a partition of the set A, B, C, D, E, F? So if you haven't read the book, you need to do so and find out what a partition is. First of all, 27 has many parts. We're just going to do part A. And 27 appears in your homework, so you'll do some of the other ones. There is another part of this that the book answers in the back, so you can get a little help with. I think it's part D, if I'm not mistaken. But the others you need to figure out on your own. So what does it mean for a set of sets to be a partition of another set? So a partition is going to satisfy two properties. One, the union of these sets needs to equal this set here, right? So the union of ADE, BC, and DF needs to be the union of these guys. And in fact, that's true. Okay, we can look at A, B, C, D, E, F, and we can find all those elements here and no extras. But the second property that a partition has to satisfy is that these sets, these three sets that are given, need to be mutually disjoint. And so that means when you take any two of them, they cannot overlap. You have an earlier homework question that's going to deal with mutually disjoint, so make sure you're okay with that definition. Mutually disjoint or pairwise disjoint means that their intersections are empty. And so we can see that the first and last of these three sets, in fact, overlap with the element D, and that's going to be the key to our answer. And so we have, first of all, no, this is not a partition, but while it is true that the set A through F is equal to the union of our three given sets, we can say that the sets are not mutually disjoint. And we should be particular about that. We should say, in particular, ADE and DF intersect to give the set D, which is definitely not empty. And so that's sufficient to show that this is not a partition of A, B, C, D, E, F. All right, and our last example in this video is going to be problem number 31. We're given two sets A and B, and we have to find some power sets. So once again, make sure you're reading the textbook and learn what the definition of a power set is. But what we're looking for in a power set is the set of all subsets. Okay, so when you're given a set, you can compute the subsets. That's an exercise that we did earlier in the semester. And if you take all of those subsets together and make them elements of a larger set, we call that a power set. And so looking at part A, first of all, we have to compute the power set of A intersect B. Now what is A intersect B? Well, A and B overlap at only one element, and that is 2. Now make sure you pay attention to parentheses and braces and commas. All of this notation is very important, and you will be deducted points on an exam or homework if you do not use that notation correctly. And so that can be a little bit bothersome on the eyes at times, and you have my sympathies when you're trying to write this stuff. I get a little bit lost in it sometimes too and have to fix some things. And so we don't just write power set of 2, we have the power set of the set containing 2, because the intersection of A and B is precisely this set with braces and a single element of 2. Now what is the power set of this single element set? We have to list all the subsets. And don't forget the empty set when you do that. So the empty set is a subset of every set, and it is always going to get listed and is always part of the power set. It's an element of the power set, and so it's listed with a comma. Now after that, the only element we can consider putting in there is the single element 2, and so that's going to finish the job. The entire set itself is going to be the only other element of this power set. And so this power set is going to include 2 elements, the empty set and the set itself too. All right, so what do we have for part B? Power set of A. And so A is the set of elements 1 and 2. We need to compute the power set of this 2-element set. And so once again, let's be explicit with what A is. and recognize that the empty set will be included. Now, whenever I have larger sets, the sets start to get larger, I like to order my elements based on their size. And so what do I mean by that? Well, since the elements of our power set are themselves sets, I find that it's a canonical order, a useful order, to order those sets by their sizes, their relative sizes. And so I've just included the empty set, which has size 0. Now I'm going to include my singletons that have size 1. And so there's a subset with only one element, namely the element 1. But there's also another subset of that size that contains just the element 2. Now that's all for the singletons. So beyond that, the only other subset we can consider is the entire set itself, 1, 2. Now, going back to our discussion about truth tables and rows in truth tables, you can see a similar pattern here. And we actually talked about this a little bit in our set theory discussion at the beginning of the semester. If we're trying to figure out how many subsets there are, it's going to be a power of 2, 2 to the number of elements. So when we only had one element, it was 2 to the first power, or 2 elements. With 2 elements, it's going to be 2 to the second power, or 4. If we have 3 elements, it'll get doubled again, and we'll have 8 elements of our power set. And so the power set is kind of a new language that is describing something we explored before, and I encourage you to go back to those notes. So I bring that up because now we look at part C, power set of A union B, and we can see explicitly that A union B is a 3-element set. And so we should expect to see 8 elements in this power set. 2 to the third power equals 8. So once again, we'll start with the empty set, and then we're going to add our singletons. So there's 1 and 2, and finally 3. Maybe. I think I have a little error here. Let's have a look. Okay. And beyond that, we have subsets that have 2 elements. Like 1, 2. And when we're doing this, it's a good, kind of like whenever you're using a distributive property, do some kind of canonical or lexicographic ordering. So I'm going to do 1, 2, and then 1, 3, and exhaust the use of the number 1, and then I'll move on to the set 2, 3. And so, as I said, we've got 1, 3, and now that's all the 2-element sets that contain number 1, so we're done with the number 1, and we're only left with the 2-element set 2, 3. Now so far that's only 7 subsets, and remember we're expecting 8. So we have the entire set itself with 3 elements, 1, 2, and 3. And so that completes the power set for A union B. All right, so we're almost done here. We've got one more. The power set of the Cartesian product of A and B. So this is going to remind us how to deal with Cartesian products. Cartesian product of A and B is going to consist of ordered pairs. 1, 2, 1, 3, 2, 2, 2, 3. So we need to make ordered pairs where the first element comes from A and the second element comes from B. So you might want to review Cartesian products. And in this section they expand on it to give Cartesian products involving more than 2 sets as well. So you could have ordered triplets, ordered quadruplets, and so on. As before, any power set is going to contain the empty set. But now we have to think about our singletons. A single element of A Cartesian product with B is still itself an ordered pair. And so this is where your parentheses, your braces, your commas have to be well organized and correct, especially since we have braces within braces. Remember, a power set is a set of sets, and therefore that notation gets nested and a little bit cumbersome. And so each of these 4 singletons is going to provide a one-element set that is an element of the power set. Now beyond that, we have 2-element sets, and as before, we want to use some kind of nice canonical ordering. And so I'm going to start with 1, 2 and pair it up with each of these guys in turn. And so we're going to have 1, 2 paired up with 1, 3. Once I fix my error. And then we're going to have 1, 2 paired with 2, 2. 1, 2 paired with 2, 3. Okay, now we're not done with our 2-element sets. Those are just the ones that used 1, 2. Now we're going to use 1, 3 and pair it with 2, 2 and 2, 3. Now we've already paired it with 1, 2 previously, so we don't have to worry about that. But we're going to take 1, 3 and pair it with the elements that appear after it. And so we have 1, 3, 2, 2 and 1, 3 and 2, 3. And then finally we have to pair together 2, 2 and 2, 3. And if you're keeping count, that's going to give us 6 subsets with 2 ordered pairs in each of them. Okay, now we have to move on to subsets of size 3. And going back to the original power set question here, there are 4 ordered pairs in the given set. That's 4 elements. And so we're expecting 2 to the 4th, or 16 subsets in our list. And so what do we have so far? We have 1, 2, 3, 4, 5. We just got 6 more. That's 11. Okay, so we need 5 more. And we have to move on to our triplets here. So what are our 3-element sets? We can take the first 3 elements. And now I'm going to keep 1, 2 and 1, 3, but I'm going to replace 2, 2 with 2, 3. Now this is all the possibilities that use both 1, 2 and 1, 3. So I'm going to keep the 1, 2 and get rid of the 1, 3, which leaves me with only one triplet possible. One, 2, 2, 2, 2, 3. And finally I have a triplet that doesn't use 1, 2. It just uses all the remaining 3 ordered pairs. 1, 3, 2, 2, and 2, 3. And we can't forget our 4-element set, which is the entire set itself. And that finishes our power set. For those 3-element sets, you could also think of their complements, since we're talking about complements of sets earlier. The complement of 1, 2, 1, 3, and 2, 2 is 2, 3. And so we expect that since there are 4 ordered pairs, their complements are going to be 4 different triple sets. So it gives you a convenient way to keep track of whether you've gotten all of your 16 subsets. All right, well that finishes our examples. I hope this is helpful for your homework. I will provide a due date for this homework when I post it on My Up in Math and send you an email. For now, we'll stop the recording.